In this video, you will learn about exponential functions and their application. Now to begin, what is an exponential function? Well, an exponential function is a function where we have f of x equals b to the x power, where b is bigger than 1 and b is not equal to 1. So for example, this could be something like this, where we have f of x equals 2 to the x power. Or it could be 3 to the x power, or 1/2 to the x power. So the exponent is now a variable. And then with this, we can evaluate. So for example, if we had f of 2, we can evaluate this exponential function where we would have 2 to the second power. You plug a 2 in place of x, and 2 squared is 4. You can do f of 4, you can have 2 to the 4th power, and that would be 2 times 2 times 2 times 2, which is 16. You could also have a fractional exponent, so f of 1/2, you'd plug a 1/2 in place of x, so that would be 2 to the 1/2 power, which would be the same thing as the square root of 2. Right? Remember, the numerator goes here with the 2, and then the 2 for the denominator is your index. So that's the square root of 2 to the 1st power, which is the square root of 2. Now, what does an exponential function look like when you graph? Well, first off, realize that an exponential function is 1-to-1, meaning it's going to pass the vertical and the horizontal line test. The domain of an exponential function would be all real numbers, because we could plug in anything in place of x. And the range is going to be all positive real numbers. And then the general form of an exponential function, you would have the y-intercept at the point 0, 1, and it's going to pass through the point of 1, comma, b. And if b is bigger than 0, so say you have like 2 to the x power or 3 to the x power, it's going to be an increasing function. Now putting this all together in a graph, what that's going to look like is something like this. All right, where this point over here on the far left, x is -2, so we have some number to the -2nd power, which is going to be a fraction. And then if you have a -1 for x for the second point, we have b to the -1st power, and that's going to be some number to the -1st power, which would also be a fraction. It's going to be less than 1 for y. If x is 0, here for the third point, that means we have b to the 0 power, which is going to be 1. So we have the point 0, 1. And then here, what we were talking about with this line is if x is 1, so that's going to be this point right here. If x is 1, we have b to the 1st power, which would be just b. So one of your points would be 1, comma, b, whatever that number is for b. And then if x is 2, we have another point up here, so that would be x is 2, and then your y value would be b to the 2nd power. You plug a 2 in place of x, and we have this other point. So we don't have a number actually plugged in for b, but whatever it is, if b is bigger than 0, the function is going to increase as you see here. Which, by the way, this function is asymptotic with the x-axis, meaning it's going to get really close to the x-axis, but it's never going to actually reach it. All right, so that would be if b is bigger than 0, and if b is between 0 and 1, all right, and sorry, that was if b is bigger than 1, it should be 1, not 0. If b is between 0 and 1, so it's a fraction, it's going to be a decreasing function, and it will look something like this. So we can do that because, let's say, just for example, let's say b is 1/2. So say we have y equals 1/2 to the x power. If that is the case, right, if x is -2, we have 1/2 to the -2nd power, which, raising a fraction to a negative exponent, you'd have to flip the numerator and denominator. So you have 1/2, so 1/2 to the -2nd power would be 2 over 1 to the positive 2nd power, which would be 4. All right, that's why it's up here high. And then if x is -1, we would have 1/2 to the -1st power, which would be 2 over 1 to the positive 1st power, which would be 2. So it doesn't go up as high for the y value when b is -1. or when x is negative 1, sorry. And then here, if we plug a 0 in for x, okay, we have 1/2 to the 0 power, which would be 1. And then if x is 1, we have 1/2 to the first power, which would be 1/2. And then if, right here for this point, if x is 2, we have 1/2 to the second power, which is 1/4. And as x increases, you get a smaller and smaller fraction, meaning it's going to get closer and closer to the x-axis. And the more negative the x value becomes, so say you have -3 or -4, it's going to be increasing in this way more and more. All right, so your function will look like this, and that is a decreasing function because it's going down in this manner. So kind of the steps we did here, assuming that your b value was 1/2, that's what we can do to graph any exponential function. So say we have f of x equals 3 to the x power, and you were told to graph this. What we do is we could plug in different values for x. So here we have 3 to the 0 power. That would be 1. So when x is 0, y is 1. If x is 1, we have 3 to the first power, which is 3. So second line, when x is 1, y is 3. If x is -1, as we see here, that would be, sorry, it's -1. That would be 1 over 3 to the first power, which is 1 over 3. So we have 3 points, which in this case is really probably enough to know what's happening, because we know the general shape of the graph. So if we plot those 3 points and connect to make a curve, it's going to look something like this. And it's going to get infinitely close to the x-axis without ever actually reaching it. And then it's going to keep going up like this forever and ever. Now, if you understand that this is kind of your basic function, your basic graph of an exponential function, we can do different things to the different numbers to translate or reflect or move the function around. So for example, you can add like a 1 over here, or you can, with the variable, you can like subtract something, or you can change this number or multiply this by something. So different things we can do to affect the graph. So for example, let's say we had f of x equals 3 to the x power minus 2. Okay, this would be your function that you see graph. That would be f of x equals 3 to the x power. But the minus 2 on the outside, that is a vertical shift. That's going to shift the graph down 2. If it were a plus 2, it'd shift the graph up 2. But it's shifting it down 2, and we get a graph that looks like this. Now if you had 3 to the x minus 2 power, so the minus 2 is up here with the exponent, this minus 2 is affecting the horizontal shift. It's going to shift it horizontally. Now the thing is, this one is a little counterintuitive. It's a minus 2, but it's actually going to shift it in the positive direction 2. So it's shifting it 2 to the right in this case. And if it was like a plus 2 up there with the exponent, it would shift it in the negative direction 2. So that would translate over to the left 2. Now what about this function? We have 2 times 3 to the x power. Well, here we see graphed f of x equals 3 to the x power. The 2, the number being multiplied outside of that, that is going to either compress or stretch the graph out. And the 2 is actually going to stretch it out. It's going to make it more steep, so to speak. So it's going to look something like this, where it's going to go up at a little bit of a faster rate by a factor of 2. So here we see that graph. And if it was like a fraction, like 1/2, all right, it would be more spread out. It would look something, I guess, kind of like this right here, if it was 1/2. All right, so the number in the front will make it go up faster or make it go up slower. So it affects like the slope, so to speak. Next we have 3 to the negative x power. So the exponent is a negative number. Well, what that's going to do is it's going to reflect the graph across the y-axis. It's going to reflect across the y-axis. All right, so when you do that, we've done this in the past, but it's going to look something like this right here. So if you're trying to sketch that by hand, you would have to find a point on the original graph. So say, for example, that was the point 1, 2. Actually, that should be, well, whatever. So let's say it's 1, 2, for example. Then what's going to happen is you have to change the x value to be a negative. So you have -1, 2. And that's going to be your reflected point. So you do that for every point, or enough points to know what's happening, and that's going to give the reflection across the y-axis. Now, another type of exponential function we want to talk about is the natural exponential function. So we have what's called the natural exponential, and we represent that with the letter e. So it's kind of like pi. So pi is an irrational number that keeps going on forever and ever, and pi was the ratio of the circumference and diameter. Well, here the letter e, the natural exponential, is a number found by doing 1 plus 1 over n raised to the n power as n increases without bound. So as n approaches infinity, basically. So you can actually experiment by plugging in some really large number in place of n. And if you plug in some really large number, the bigger the number you plug in, the closer that number is going to become to this number right here, which is approximately 2.718, and again, that number is irrational. It would keep going on forever and ever and ever. So the letter e is called the natural exponential, and this is used in different applications in math. But for now, we're just going to work with it a little bit. All right, so a function that has that letter e in it is called a natural exponential function. All right, so for example, here we have f of x equals e to the x power. If you were to graph this, it's going to look just like all your other exponential functions. It's going to look something like this, because you plug in different values for x, and we're going to get some number, right? It'd be like raising 2.7, if you round that, it'd be like raising 2.7 to the first power, raise 2.7 to the second power, raise it to the third power, to find these points, and then we get the graph as we see here. So we're not going into too much detail with the natural exponential for now, but at this point just realize that it exists, know what it is, and then realize that the graph would look basically the same as any other exponential function. And here we're going to work with just one example problem, so using the natural exponential function. And what we're told here is that the number of bacteria in a culture is given by the function n of t equals 930 times e to the 0.3 times t power, where t is measured in hours. And the question is, what is the initial population of bacteria, and how many bacteria will the culture contain at t equals 5? So basically all we're doing is we are evaluating this function. All right, so we take the initial function that was given to us, and the initial population, so that would be when time is 0. So what we do is we plug a 0 in place of t to figure out what is the initial population. So if e to the 0.3 times 0 power, which is e to the 0 power, and anything to the 0 power is 1. Doesn't matter what the number is. So that would be 930 times 1, or 930. So the initial population is going to be 930. Now the next part of the question says, how many bacteria will the culture contain at t equals 5? So this would be after 5 hours. So we plug a 5 in place of t into this function. So we have 930 times e to the 0.3 times and then 5. Well, 0.3 times 5 is going to be 1.5. So we have 930 times e to the 1.5 power. Now to do this, you definitely need a calculator of some sort, and we'll show you in a moment what that would look like on Google, so a Google calculator. But most calculators would have an E button. So you look for the E button, raise it to the 1.5 power, and then multiply by 930. So that would be 930 times 4.48, which would give you 4,166.4. So that would be the amount of bacteria after 5 hours. Now to finish off the lesson, I want to show you quickly how to type in the letter E to some power in a calculator, and also how to put into a calculator something like maybe 3 to the 4.5 power, or some number raised to any power. All right, so we're going to show you that quickly with Google Calculator. So to access Google Calculator, what you do is you just go on to your browser, type in the word calculator, and then up comes the Google Calculator. So you can use the Google Calculator, you can use some other type of calculator, whether it be on your phone or on your computer, or it could be an actual calculator. Either way, it's going to be pretty much all the same thing. The button might look a little bit differently for the exponent button, but so your calculator, make sure you find where the button is, and then this is what you would do. So let's say you wanted to do, let's say 3 to the 4.2 power. All right, so what you do is you type in 3, and then your exponent button would be right here. So this x to the y power here, that is your exponent button. Sometimes your calculator might have a little caret symbol, so like what you'd see on your computer, Shift and 6, that little caret symbol, that would also be used sometimes on some calculators. But say you're trying to raise 3 to some power, what do we say, 4.2, you can raise it to any power, just press equals, and there is your answer. So it's very quick here on Google Calculator. Just type it in. So you can do that with any exponent. You can do fractional exponents as well. And then the natural exponential, we see here the letter E. So we do E, and then every calculator is a little bit different. So you want to raise E to some power. So you want to do E to the second power. You push your exponent button, and then you type in the number 2, or whatever you want. It could be 2.3, it could be whatever, and press equals, and that gives you your answer. And if you do like E to the first power, we can verify with the calculator that that is equal to the 2.718281, etc. that we gave in the lesson. So it's very quick, pretty straightforward, I feel, with the calculator. You just need to figure out where those buttons are on your calculator. And that concludes our lesson for today. We will see you next time.